So what is the problem when you throw out one thread and bring in another thread? What do you need to do? So where is the dynamic state of that thread being maintained? There are hardware registers where it has fetched data, kept it in the registers, it's doing some computation on it, right? For data which is fetched from the memory, the register contains copy of the data in the memory, right? At the end of the day, this data is supposed to go back to the memory location, right? If some update is performed. So now each processor has some data registers and it's doing some computation. Let's say it was supposed to do some addition and then it was supposed to do some multiplication. It did the addition, suddenly it got thrown out. So what are the actual assembly instructions? So the assembly instructions will look something like this. Add to register 1 the value 5. Multiply register 1 with 10. Something of this sort, right? This may be what the code looks like. Now suppose the thread was executing this instruction, add r1 comma 5. Right? So it was adding 5 to r1. So it added 5 to r1 and then the operating system decided I need to schedule this out. Okay? Its time slice got over. So another thread comes in. Maybe that thread is using register 1 for some other purpose. So it's going to replace the contents of register 1. And now when this particular thread comes back, it comes back and starts executing multiply r1 10. But now it has some other data. Right? So obviously we don't want this to happen. So whenever a thread is scheduled out, right, that is called a context switch. Whenever a context switch takes place, a copy is created for all the registers and kept in some space which is thread local space. Right? So there will be a thread local space for thread 1, there will be a thread local space for thread 2 and so on. So every thread will have some local space. So now what happens is that when this thread 1 is getting scheduled out, at that time all the registers will be copied into the local space of the thread. This is in the memory. So you're copying the value from the registers to some memory location. So this is copied into this particular memory. And then let's say thread 2 is getting scheduled in, it's going to pick up all the registers for thread 2 and put them into the actual hardware registers. And then it's going to start the execution of thread 2. Okay? So that way what happens is that a thread always maintains its state. Right? So whenever the context switch happens, its state is saved, and whenever it is scheduled back, the state is copied back into the hardware registers.
We maintain different stacks always.
Yeah. So you could possibly maintain the stack also in the thread local space. Right? You could.
We need to copy the contents of stack also.
No. This is your main memory. I've created some space for thread 1, right? I'm maintaining the stack for thread 1 and I maintain other things as well. Okay, I'll talk about what those things are. I maintain some space for thread 2 and I maintain the stack for thread 2. This is the memory, right? Clear? Now there is the processor, and the processor has registers, register R1, register R2, register R3, program counter, stack pointer, and so on, right? It has lots of registers. Limited set of registers, right? You can't have arbitrary number of registers. It's quite costly. It's very close to the processor, right? The arithmetic and logic unit directly works on registers whenever it has to do addition, multiplication, and so on. Let's say you have an integer x with value 5 in the main memory and you want to, let's say, increment it. You want to add 1 to it. You can't go and add 1 to it in the main memory. What do you have to do? You have to fetch it into a register, let's say R1, add 1 to it, and then put it back. You only have a limited set of registers, maybe just 32 registers. That's just about all you have. Main memory is in gigabytes. When you switch the context from one thread to another, the main memory is still there. Right? It's huge. It has enough space to store data for thread 1 as well as thread 2 and 10 threads. And global variables and code and everything, right? It has enough space. What is the problem? The problem is the registers. The processor only works on the data that is residing in the registers. Whenever a thread gets scheduled in, it needs to know which stack it's working on. So that is done by a register called the stack pointer. The stack pointer just points to this particular stack, stack 1. That's all. All the contents of the stack are not in the registers. You just have a pointer to the stack which is kept in the register. Okay? So now when the thread gets scheduled out, what do I need to save? What state space do I need to save? So there's no problem with the memory. Where is the problem? The problem is with the registers. I need to save the value of the registers because one thread may require as many as 30 registers, right? But I don't have 30 times 10 registers for 30 for each thread. I don't have so many registers. So that's why I need to save the state of all the registers somewhere in the memory. Remember, I had this space for each thread. I'll go and save it over here. Right? So this is the thread context. So I'll store the registers over here. Alright. And now once I've stored the registers over there, these registers are free for use, right? Anybody can come and use them because I have saved my state. Whenever I get scheduled next, I will copy it back. I'll copy this data back so that my registers are up to date, right? My state is the same. And then I will start executing the instructions. So what does that mean? Even the program counter goes here, even the stack pointer goes here. Which instruction was getting executed, that is also saved in the thread context. Which stack corresponds to it, that is also stored in the thread context, right? Now when thread 2 comes in, its data from its thread context gets moved into the registers, which means that now the stack pointer will be pointing to its own stack and the program counter will be pointing to the instruction that it was executing last when it was scheduled out. Main memory, I don't need to bother. I don't need to save state of main memory. Okay, I need to save the state of registers. All right. So the number of registers is small, but a context switch is still costly, right? Because all these registers need to be backed up into the memory, and the registers of the new thread need to be copied back into the registers. So this is a time-consuming operation. It takes time to do this. So that's why typically the time slice is not so small, right? There's a trade-off in the time slice. I want to execute many threads in parallel. I want to give them short time slices so that I get the feeling that there are more tasks running in parallel, right? But at the same time, I can't make it too small because otherwise the context switching is going to start taking time. Yeah.
So when we are doing a context switching, anyway we are moving our registers from the hardware to the memory, from the CPU, from processor to the memory. Why don't we update our stack values at the same time for the local variables? Because they have been changed in the registers. Same memory is not being copied into our memory. Anyway we are doing.
So there are several things over here. But the most important point is that these are not directly related. I mean, I don't know what is there in my register, right? The compiler knows that. Look, this is the work of the compiler. The compiler figures out that what am I supposed to keep in what register. And it generates code of this sort. Add R15, mul R110. So it knows what have I kept in R1. It has kept track. When I said multiply x by 10 or add 5 to x, it kept track. Before this, it will have an instruction load R1 with some @1002, which is actually the location for variable x, right? So this is all being done by the compiler. At runtime, I have no way of figuring this out. When the thread is getting executed, for it to figure out that, what is stored in R1, oh, it's the variable x, it's not possible. It has no clue whatsoever. Okay, the compiler has the complete picture and it has generated the code for that. But the point is, at this point of time when I have scheduled this thread out, I have no way of knowing up ahead whether a store instruction is coming or not. Right? And for me to try to figure that out is challenging. There are lots of issues in doing that. So to keep things simple, all you do is that whenever thread goes out, save all the registers. Whenever it comes back in, bring back all the registers and start executing exactly where you left off. And that causes no problem to the compiled code. Whatever register it was working on, it will find exactly the same value in the register. Okay. The only issue over here is, yes, it takes time to do the context switching, to save all those register values and bring them back. So this is how multiple threads execute on a single processor. There is context switching that happens either based on time slices or the threads making blocking calls where they don't need the CPU resources for some period of time and therefore they are moved out. So you get the impression that multiple threads are executing concurrently at the same time, right? Whereas there's just a single processor which is executing them all. Let's come to multi-core architectures. So what happens in multi-core architectures? So in multi-cores, you just have multiple processors, each with its own register set. Let's say you have 4 cores and you're executing up to 4 threads. You will see that the operating system will just schedule them on separate cores. And there's no context switching that happens. All of this is with a caveat. There are some daemon processes which wake up from time to time and do some stuff. So they may schedule out your threads and do some work. But barring that, you will find that you will get good utilization of all the cores with different threads being allocated different processors. Okay? So if you have 4 cores and you're running up to 4 threads, you'll see very good performance. Sometimes to avoid these daemon threads and all, we try to run a fewer threads than the number of cores. So next time when you're trying to execute some parallel code, you should understand what the underlying architecture is. Only then you'll be able to figure out that what kind of performance gains you're going to get, right? Is it a single core? And if you're doing something computational heavy, you're not going to see much gains with multiple threads. But if you have multi-cores, you'll start seeing the gains.